Okay, let's get started. Welcome to the final lecture of the class. We will have 2 final exam review sessions held next week. The TAs are still deciding exactly when. We'll announce it, and hopefully we'll even, record it for those that can't make it. So, a few things that we need to cover in this class, and then we have a fun demo. All right. So first of all, we have differential equations that can be solved with the Laplace transform, and that's going to lead us to some cool control applications. All right. So here's here's what we wrote last time. If you have a sum from k equals 1 to m of derivatives, actually k equals 0 to m, of ak times derivatives of x of t, and if that equals some linear combination of derivatives of y of t, actually, does someone remember, did I use a's as the coefficients for x or for y last time? I will make it consistent here. And I had it, the y's had the a's. Okay, so let's do that. All right, so and we saw that this constant coefficient linear differential equation can be solved easily by doing a Laplace transform on both sides. And we immediately get knowledge about the frequency domain of this signal. It becomes bk, derivatives become s to the k. Whoops, those aren't to the k, that's a sub k. And then we just factor out because it's multiplication, and we get that y of s over x of s, which you recall is the transfer function of the system, that equals sum of the b's, yes. And we see that it's a rational function, which if we then factor, we can find poles and zeros, and we've been focusing our attention on rational transfer functions for this very reason. Okay, so we also have something called a difference equation, which is the discrete time analog of this. And here you get things of this form. As an example would be like x, like suppose that y of n equals some linear combination of the past inputs. So let's say 3xn plus 2xn minus 1, and also some of the past outputs. All right, so it would be like minus 1/2 y of n minus 1. Okay, so this is a difference equation. And you see that the impulse response of this will usually be infinite in duration. Okay, if you put a delta function in at time 0, you get some feedback, and the past outputs cause future outputs, and so forth. All right, and so this sort of a system as well, you can do the same sort of tricks. So let me write, the general expression would be a sum of, let's say, ak times times y of n minus k, all right, equals a sum bk times x of n minus k. So we could rearrange these constant coefficient difference equations into this form. And then we would get the same type of thing, because if we take the z transform here, by linearity, we bring it right in, and we get, and delays in the z transform just become z to the negative k of y of z. Okay? All right. So here we get something in z inverse. We get that y of z over x of z equals sum of the bk's times the z inverse z to the negative k. Okay, now if you want it to make this look like a standard rational function, multiply by z to the m on top and bottom. You'll get positive powers of all the z's. Sometimes it's just convenient to do z transforms in terms of z inverses. Notice if I had redefined this difference equation to be plus k instead of minus k, this would all be positive z's. But anyway. Okay, so then immediately we see that we can get poles and zeros, and we can know whether a system is stable. We can know things. We can interpret the Fourier transform if it is stable by looking at the appropriate location within the Laplace transform. So for example, in the continuous time, we would get the Fourier transform by looking at the imaginary axis. In discrete time, we would get the Fourier transform by looking at the unit circle. Okay? And if we want to know in the time domain what the impulse response of the system is, then we have to do an inverse Laplace transform. All right? It's a little more work. Getting the frequency domain is very straightforward, and then do a little bit more work and you get the solution in the time domain. Okay, so let's do, we had an example last time which was the following. It was just a simple, we had a sum, we multiplied by 5, and we put it through an integrator. And we fed it back like this. Okay, we called this x of t and this y of t. And we ran through and got some equations. Now, I'm going to do the same thing again, but this time I'm going to take Laplace transforms first. So I'm going to say, okay, this is x of s. This is y of s in the Laplace transform domain. By linearity, this is x of s plus y of s. All right, and then by, and so then we get times 5 here, and then the integral just becomes a times 1 over s. So an integrator in the Laplace domain is just 1 over s. It's just multiply by 1 over s. Right? All right, so 1 over s times 5. Better make my 5s look different than s's. Okay, and then we get our equation. Same thing we ended up with last time. We get y of s equals 5 over s. And we want to solve for y of s over s of x of s. So we'll start by multiplying both sides by s, subtract one term over, and you get s minus 5 y of s equals 5 x of s. So I multiplied both sides by s. Let's just check that. Yes. Subtracted the 5y of s from both sides. Therefore, this ratio is just 5 over s minus 5. And we saw that it has one pole, no zeros, and that one pole is located at s equals 5. Okay, so what can we conclude then about this system? Well, is it, okay, assume causal. So if I really build this such a thing, what's going to happen? Well, it will be causal. So here's if we plot the poles in zeros, we get that it has a pole at s equals 5, right? So the region of convergence, being causal, the region of convergence has to be to the right of this. Here's the region of convergence. And it is not it is not stable because it does not contain the imaginary axis. Okay, so this is an unstable system. Well, looking at this system without doing any Laplace transforms, you should have known it was unstable. If you think about what's going to happen, put a little bit of an input in. This integrates the input and then gives positive feedback. In other words, it adds the integral back over to the input. So you can imagine that this is going to keep accumulating more and more, get bigger and bigger. And we can calculate, let's calculate exactly what the impulse response is, because we have the Laplace transform right here. And we know from our table of a very short list of Laplace transforms that we're going to use that the inverse of this is just e to the 5t u of t times 5. Because you remember, e to the at u of t went to 1 over s plus a. Of course, we used the fact that it was the region of convergence was to the right. If the region of convergence was to the left, we have a different left-sided signal with the same Laplace transform. Okay, so this is what comes out, and now we have some intuition of what would happen if you hooked up this positive feedback loop on an integrator. It's going to blow up exponentially like this. Right? Okay. Let's do another example, this time in discrete time. All right, so suppose I have something like this. X of n comes into some system which is doing the following. Just a minute as I draw this. An 11 there, a 3 there, 2 here, and we'll put a 1/4 here. Okay, so here is a different block diagram. And these D's, what I mean by D in the discrete time case is this is a delay of 1. So in other words, it's just a memory element. It stores what was the input and outputs it for the next time unit. Okay, so we're saying our input signal gets delayed, and there's some summation that's going on, and then y of n is output, but you see y of n is also stored for 2 time periods, right? The last y of n, so we can go labeling some things. This here then is y of n minus 1, and this here is y of n minus 2. Okay? Of course, when the node splits here, it's the same signal goes both directions. So the input to this sum is y of n minus 1. The input to this delay was y of n minus 1, which is why we got y of n minus 2 out. Right? Okay. So then we can get some other things here. We can say, we can start putting labels like that this is x of n plus 3 y of n minus 2. Okay. And finally, we get that this thing here is, well, I guess I should label this as x of n minus 1. All right. So we get 2x of n minus 1 plus what came into the node from the left, which was x of n, plus 3y of n minus 2, and then plus the part that comes in from the bottom, which is 11 times y of n minus 1. Okay. Now that all gets multiplied by this 1/4. So I could rewrite this whole thing with a fourth around it, and what I'm going to get is our equation, our difference equation, which is that y of n equals 1/4 times this whole thing that I wrote up there. And of course, we can take this to the z domain. My usual habit would have been to do that up front and just write all of this in terms of z transforms, but it doesn't make any difference. And we would get that another approach would be we could write it in this standard form up here and just use this result. Okay. In fact, let's go ahead and do it that way. So we'd get y of n, and we have, well, let's multiply by 4. 4y of n minus 11 y of n minus 1 minus 3y of n minus 2 equals x of n plus 2x of n minus 1. All right. And finally, that's going to give that y of z over x of z is going to equal 1 plus 2z inverse over 4 minus 11z inverse minus 3z to the negative 2. Okay. So let's locate the poles and zeros. Okay. First of all, we should factor this. Well, we can say that this, multiply both by z squared, just to get it into positive powers. So we get z squared plus 2z over 4z squared minus 11z minus 3. You can do everything in terms of z inverse, but I just want to keep it simple here. And that factors like this, z plus 2 times z over 4 times z minus 3 times z plus a fourth. Am I right about that? Yes, I think so. Okay, so now of course to do this factoring, you either do whatever tricks you know, and if you come to your last resort, use the quadratic formula here, and you'll get the roots. So what can we say about this system? Let's look at the locations of the poles and zeros. We know that it's got poles at 3 and at negative 1/4. Go ahead and put them here. This is 3 minus a fourth. All right. And where are the zeros? We have a 0 at negative 2 and a 0 at the origin. Okay. So how do we decide whether this system is, well, again, we're assuming causal. Anytime I come from a block diagram, I'm assuming I'm implementing this thing in real time, so it's a causal system. Assume causal, okay. Then what should I do here? Can I determine the region of convergence? What's the region of convergence? So z is complex, so how should I do z is greater than 3? Yes, the magnitude of z. If it was Laplace, if it was continuous time, it would be the real part that I would compare. Right? So in continuous time, I'd compare real parts and I'd get vertical lines. But here I'm comparing magnitude because it's discrete time, because it's the z transform. So the magnitudes define, there are a couple possible regions of convergence. Oops, that needs to go over there. And one would be defined by this pole. But we know it's right-sided, so we know we're actually out here, right? That's where we're converging. Now, how do I decide, so here's the ROC. How do I decide if it's stable? Yes? Good. And the unit circle is inside, and the region of convergence is outside. So this is unstable as well. What does it mean that this is unstable? If I put a delta function in, it means that as you can follow what would happen. You can try to get the impulse response little by little, and that's actually quite easy. You can follow this through and put a delta function in, which means a 1 at time 0, and then all the rest of the time it's 0. And you can put what goes in the delay units and everything and do the calculations and step it through one step at a time and get the impulse response one step at a time. That's very easy for a discrete time system. All right? You won't necessarily get the formula for it, the analytic expression that way, but you'll get samples of it, right? And what we would see is that because of the feedback, these samples, they might oscillate, but they'd start growing and growing. They wouldn't die off. And that's what it means to be unstable here. Okay, we also can look at some other, well, actually, yeah, not in this example. Okay, fine. So I want to show you now how you can actually get the time domain of this, how you can do the inverse transform of either Laplace or Laplace or Z transform. Okay, so technique will be partial fraction expansion. And all that means is we have these rational functions. And we want to turn them into sums of single pole fractions. Okay? So let's see how well it'll work in this case. So for example, this Z transform, let's take this one that we just did. Right here. So we have h of z. I'm going to rewrite it here. For convenience, I'm going to put it in terms of z inverses. I mentioned we could do that before. Here, I'll show you that it'll be less work if we do it that way. Okay, so I can divide my z squareds out. Right, and I get that this is 1 plus 2 z inverse. And this is 1 minus 3 z inverse. It's 1 plus 1/4 z inverse. Okay. I want to write this as something a over 1 minus, oh, did I get all the terms here? No, I need a 4. Yeah, I need a 4 here. Okay, so I want to write it as 1 over a over 1 minus 3z inverse plus b over 1 plus 1/4 z inverse. Now, of course, we know that if we add these two fractions, the denominator will be the product. Think of this 4 as being a 1/4 in the numerator. And so if we choose the right a and b due to the cross multiplication, we should be able to reconstruct this fraction. Okay. So now you can just do whatever solver you want to get A and B. For example, you can write out, you can multiply it out. If you multiply this out, you'll get a function. The numerator will be some function with A and B in it. And you equate that with the numerator over here. And you match up the parts that have Z inverse. And you match up the parts that don't have Z inverse. And you solve this system of equations. Okay, linear system of equations, you find A and B. There's a trick I'm going to teach you. I'm going to assume you know that method, that you could do that if you need to. The trick that's a little faster is referred to as the cover-up method. And what that says is, this trick, by the way, well, okay, I'll show you the trick, and then I'll tell you all the little caveats of when it might not work. But the trick is this. You say, I can find A by doing the following. Notice that, well, okay, I'll do the trick, and then I'll tell you why it works. I can cover up you see this denominator term in A? I can cover it up in this fraction. So I put my hand over it like I'm temporarily deleting it. Okay? And then I say, and then I plug in the value for Z inverse that would have made this term 0. So the value for Z inverse that would make that term 0 would be 1/3. Okay? So I plug in 1/3 for all the other places where there's a Z inverse. All right? So the top becomes, pretend my hand's there, but you can't see it. Okay. So this becomes 1 plus 2/3. Right? Okay. This becomes 1 plus 1/12. All right. And I still have this 4 here. So I end up with A equals 1 plus 2/3 over 4 times 1 plus 1/12. All right, and then whatever, multiply that out. Now for B, I would do the same type of thing. I would say B equals, I would cover up this second term here and plug in Z inverse equals -4. Right? Because Z inverse equals -4 would make this term 0. All right. So plug it into the rest, and you get something like this. 1. Now I'm plugging in -4, so it's 1 minus 8. Over 4 times 1 plus 12. Is that right? Yep. Okay. And now I have A and B. Again, I just calculate out these numbers. So I've expanded this fraction into those. Okay, so use whatever method you need to. You know enough ways to do this. And the point is that once we've changed it to this sum of fractions, we have in our handy little short table of Z transforms, we have this exact one. All right. So we just simply use that our knowledge that we have to use the region of convergence when we invert the Laplace or Z transform, right? And the region of convergence is outward. It's the right-sided region of convergence. So we take the right-sided Z inverse. For both of these. Okay. And if you recall, that means that h of n is going to equal a times -3 to the n u of n plus b 1/4 to the n u of n. Did I do that inverse correct? With the minus signs? I think so. Is it 1 minus AZ inverse or 1 plus? It's 1 minus AZ inverse. So then these minuses need to go away here. So this is just 3, and that's -1/4. Okay, so we've just solved explicitly what the impulse response is of this system. Not too much work. Again, getting the frequency domain was really easy. It just required factoring to find the poles. Then you do partial fraction expansion if you want to take it to the time domain. You will find the same thing happens in the Laplace transform, so we won't go through that exercise. Okay, partial fraction expansion, then look it up. However, a few things you'll notice. First of all, you must make sure, the numerator is lower order than the denominator. Okay, so if you don't, then you're not going to, your system of equations won't have enough variables. Okay, so you won't be able to do it this way. You won't be able to do a partial fraction expansion. Now, you can change this a to be something like a z inverse plus b in the numerator. That's not the way I would suggest doing it. What you should do is first reduce your fraction using one step of long division, or however many steps it takes to reduce it. And I will do that example in a minute. Okay, but you see here the numerator, in terms of z inverse, the numerator was lower order than the denominator. If I had done the partial fraction expansion in terms of z, of course that's perfectly valid. Here, though, notice the numerator is the same order as the denominator. So I would have to do one step of long division to turn this into two terms. One would be a constant term, and the second one would have the same denominator, and the numerator would be just zeroth order, right? Or first order. Okay, and then I would do my partial fraction expansion. The other thing is, if you have higher order poles, by that we mean, what if you have two poles at the same place? Okay, so you've got two of the terms in your denominator are the same pole. So you usually would write that as one of them squared. Okay, how do you do that partial fraction expansion? Because now you have too few terms over here. Are you going to write it twice? That doesn't do you any good, right? So then what you do is you have two. So if you have a 1 over, or if you have some function n of z, the numerator of z over something like a 1 plus, or 1 minus az inverse squared, what you would do is you would write that as an a. You'd end up with two terms over here, 1 minus az inverse, and the other one would be 1 minus az inverse, well, squared. So I'm assuming you have other poles down here too. So you've got 1 minus, sorry. So say you have a 3-pole system, and one of those pairs of poles are the same, so higher order pole. Then you would do an expansion that has these three things. So you would have one term for each of the poles, and then you'd have one second order term. And this is enough to find an A, B, and C that match. Okay. Now, in this case, and then you of course can look this one up, we know as well. We know the Z transform, that's also in our table. All right. Now, in this case, you can sort of use the cover-up method, but not entirely. So you can use the cover-up method to find the coefficients for the highest order poles in the groups, like for B and C, but you couldn't use it for A. Yeah. Okay, so anyway, but you could always just write out a system of equations to find A, B, and C. All right. Should I explain why the cover-up method works, or does anyone care? No one seems to care. You can figure it out on your own if you want to know why that works. All right. Okay, so now we know how to go from like a block diagram or something to the Laplace transform, or maybe from a differential equation to the Laplace transform, and then how to take that to the time domain with an inverse. Yes?
Sorry, for this particular example, would it be valid to take different pieces of each of z by a transform and then convolve them in time?
Oh, because you're saying products. If you could do the convolution in time, that would be valid. That's an okay way to do it. What was that?
It's like a lot of them look like
Yeah, so you could, so that's one thing you could do. You say, well, here's a product, like you're saying. So do an inverse on them separately and then do convolution. I think it'll be more work because the partial fraction expansion isn't too bad. It depends because they're u's, you're right that they're u's, but they're u's times an exponential. This isn't a constant here, right? This is a growing function. So doing this convolution would take probably more work. But yeah. Okay. One other thing in discrete time. So let's do that. Let me show you what the long division method is. So let's say I take my example here. And I want to calculate, let's say, a right-sided or left-sided inverse to this. So I'm going to do the right-sided inverse. Of course, that depends on the region of convergence, which one you should be doing, right? And so I will take h of z, but I'm not going to take it in the form I factored it as. I'm going to multiply it back out, take it in its original form, which was up here. All right, so right there. Z squared plus 2z over 4z squared plus, what was it, 3? Minus 3. Okay. So what I can do is I can say, look at what happens if I do, if I just try to divide this out like you would do division, long division. You would say, divide this thing, z squared plus 2z, by this. And I would say, well, first of all, let me worry about the z squared term. What should I multiply by the denominator in order to get that z squared term? I should multiply it by 1/4. Okay. If I multiply by 1/4, then let me write down what I actually get down here. I get z squared minus 11/4 z minus 3/4. Okay, that's what I got from the 1/4 term. And now I can subtract this out to get my remainder. And I'm going to get something of a lower order, right? So I'm going to get, what is that? 8 minus 3/4 z, or no, plus, sorry. Negative cancels. 19/4 z plus 3/4. Okay. Now, I'm bringing up this method for two reasons. One would be I could continue to do this method and get another term. So now I say, okay, this is the remainder, so divide this by this. Try to cancel the highest order term again. In other words, what do I have to multiply by this so that the highest order z term is 19 over 4z? And what I should do is do 19 over 16 z inverse. Okay. So if I had that, then I would have 19 over 4z minus, and then I just continue on. This is 11 times 19 over 16. And the z's cancel here. Minus 3 times 19 over 16 z inverse. And again, I would subtract. I'm not going to do this here. And these two would cancel, and I'd get something that was constant plus a z inverse. Okay? And I could just continue this indefinitely, and what I would get is more and more terms, each of them with more and more z inverses on them. Okay? This immediately does go to the time domain. If I rewrite this division, okay, this fraction, as this sequence, that's what I've done here. I've done this division as an infinite sequence. But of course, the z inverse of each of these is very easy, right? So let's do the z inverse transform. That's just 1/4, and this transforms to 19 over 16, h of, hold on, what am I doing? Nope, delta, that's what I mean. Delta of n minus 1, and this one's a delta n. That makes more sense. So what I've done is I've found a way to do the inverse using long division where I get one sample at a time. It's very much like if I would have ran the impulse through my block diagram. Same method, we'll get the same answer. So this long division doesn't give you a formula for the inverse, but it gives you one sample at a time of the inverse. Notice that I got the right-sided inverse. Any ideas how to get the left-sided inverse using long division? It might help to write this in the reverse order, 2z plus z squared, and write this in the reverse order. And again, focus on now the lowest order term. So in other words, you just flip these around and you always make the left one. You find the product that would turn the left term into the left term of what you're dividing out. Okay, so just flip them in order, do the same process, and you'll get the left-sided inverse. Now, the other reason you might need to do this long division is, remember I said you can only do partial fraction expansion if the numerator is a lower order than the denominator. Okay, so if you just did one step of this expansion, we could write that this equals, let's assume we just did the first step and we got to this remainder and we didn't do any more steps. Okay, then that would equal 1/4. That's the first term up here. Plus 19 over 4z plus 3/4 over. Okay, and now that's how we've reduced the numerator to a power that's lower than the denominator. So now we do our partial fraction expansion. Okay, so if you ever have a case where the numerator is higher or equal order as the denominator, you have to do this until you reduce the order. So you can do the partial fraction expansion. Okay. What else? All right, what if you want to talk about the... okay. I want to remind you that you can take poles and zeros of a stable system. You can analyze the Fourier transform just from the poles and zeros. So let me remind you, we've talked about this before. But if you suppose we've found the poles and zeros of a particular system, we found it to be stable. Let's say this is a Laplace domain, so it's continuous time. And we found that the poles are in the left half plane. The signal is causal. You may also notice I always put poles and zeros in conjugate pairs. Any real system will have that behavior. Okay, and let's say I have some zeros here. Now, aside from knowing it's stable, I might also like to know what's the frequency response of the system. So I would go calculate the value of the Fourier transform. Now, we know that the magnitude of any point in a rational function is the distance to the poles. It's the distance to the zeros divided by the distance to the poles. Right? We derived that earlier. So just by by eye, if you didn't care to be precise, you could get some sense of how this Fourier transform is going to behave, how the magnitude will behave, right? For example, we know that at least when it gets near the 0, it's going to kind of dip down. So whatever it is, kind of dips down around here. And if there was a pole near the imaginary axis, then it would go upward near that pole. Right? Okay, this blue line is meant to be a plot along the imaginary axis. So, for example, let's go to the z domain, and I'll ask you a question here. Let's say we have z. Suppose that here's the unit circle. And if we have a pole right there and right there, and just for fun I'll put a 0 as well. And if I asked you where the magnitude of the Fourier transform is at its peak, could you determine that quickly? Maybe I don't care to find exactly where it's at its peak, but approximately. Where would you say? In other words, which frequency is amplified the most here? Sort of has a resonant frequency. All right, you're saying 3/8, yes. Okay, so you're saying basically look along the unit circle and find where you're closest to a pole. Of course, all the poles and all the zeros affect the magnitude, but if you're very close to one pole, you're going to be very large in magnitude. Okay, so that means you would expect that around here and around here, you're going to have a pretty high magnitude of the Fourier transform, and that's going to be accurate. So what Victor said was take this straight line and say, oh, that's that frequency. Remember, the Fourier transform here's f equals 0, f equals 1/4, f equals 1/2. So this is something like approximately f equals, f approximately equals 3/8. And so that would be a good estimate of the peak, the resonant frequency of this system. Okay. Similarly, if you had a 0 near it, you would expect a low point in the Fourier transform. All right. So from the poles and zeros, you can learn several things. And the one other thing that we see because of partial fraction expansion, aside from getting the frequency response, we know something about, very quickly, we know something about how this behaves in time. Because notice that when you do the expansion, you're going to turn, all of the poles are going to get their own term. Remember, we expand a fraction into sums of terms, each with the poles of the system. And each of these you'll invert into a separate time domain signal. Okay? So what that means is that if we can interpret a pole very quickly as a time domain signal, then we know that, for example, the impulse response of this system will have the time domain properties of these 3 poles because it will have 3 different terms, each with one of these poles. And if you look at it, you remember you have that 1 over s minus s pole 1 transforms in Laplace inverse to e to the, oh, that's a plus, e to the minus sp1 u of t. So the real part of this pole is the decay in the time domain. It's how quickly does the impulse response decay. And the complex part of the pole is the oscillation. Okay, so what this means is just by looking at this, I can say, oh, in the time domain, the impulse response, if these poles are very far from the imaginary axis, that means their real part is very negative. Have I done the negative signs right? Yes. So that means the real parts are very negative. That means it's going to decay very quickly. You might call that a quick response. You might say the system is very responsive on a fast time scale. if the poles are very, very much negative, if their real parts are negative. Now, if they have an imaginary part to the pole, that becomes a sinusoidal oscillation in time. Okay, so they have some sort of resonance as well. Okay, I'm just trying to give you some intuition about how to interpret poles and zeros in a way that's meaningful. We can look up, remember when we were talking about filter designs, we had we have this Hamming filter we used as an example. And if I go back to that page that we've looked at before, oh, and that's not what I want. Sorry. Butterworth. Yeah. Okay. You might remember we looked at the Butterworth filter as an example of a filter design, and I showed you a plot here. As they're going through all the characteristics, they're showing that here's the gain, the magnitude of the Fourier transform, the group delay, and so forth. They also have this plot over here. And now we know what this is. This is a plot of the magnitude of the Laplace transform. So you see the Laplace transform here has 3 poles. And the Butterworth filter happens to put those poles on a circle. You don't have to, but that's how it's designed. And the goal of the Butterworth filter is that it's a low-pass filter that roughly these frequencies, the imaginary axis, are going to get passed with high amplitude. And once you get away from there, the amplitude falls off. Okay? So this plot of poles becomes useful in understanding the frequency response of this filter. And other low-pass filters have other configurations of poles and zeros. So some low-pass filters will put zeros out here to get a very fast transition from the part you want to pass to the part you don't want to pass. They'll put zeros out here. Okay. Anyway. Okay. Time to move on to what everyone's been waiting for. All right, so we have a demo of a pendulum. And you see it's right over here. Oh, probably been. You see, just swings freely. This pendulum has a motor on it that'll turn the arm like this. And it also has 2 sensors. It has a sensor that senses what angle it's at. I'll call this the position. And it has another sensor that senses what angle the pendulum is at. Okay. So I'll probably log me all out.
It's not like you're just rotating the pendulum until it's up there.
What'd you say?
It's not like you're just rotating the pendulum until it's up there.
No, yeah, you don't have any motor on this. So we have no control over that part. Only this part. So the idea is that we want to invert the pendulum. We want it to stand like this, and we want it to hold itself up. If anyone wants to try, show us how good you are. Actually, the first thing we're going to do is just demonstrate how the motors work. And then in the end, our goal will be that we want to have it automatically use feedback and hold itself up. How many of you have seen this demo here? Quite a few of you. We like to pull it out for open houses and stuff. All right. So let's see. Oh. So first of all, I'm going to do this. Okay. So first we'll just get this motor to move. I'll even take this sensor off. And I'll pass this around so you can just feel it. And try balancing it on your finger or something. All right. Oh. So as I said, we have 2 things coming out of this system. We have a position sensor, and we have the angle. And what we get to put in there is a signal that will be torque on the motor. Okay. Great. For your reference, here is this angle here we call position. And then we have some pendulums like this. And we have, this is the angle. And so we have a little motor here. And this is just a hinge. All right. We also are going to have some input signal. We'll worry about that later. Let's see if I can get this thing to... By the way, if any of you want to take any videos while we do this and send them to me, I'll put it on the lecture video. I'll integrate it in. All right, so this is Simulink. It's just a part of MATLAB. It's an add-on to MATLAB. And it's going to be interfacing with this device. So the first thing I want to do is turn our input signal off, which I have. And I want to set some variables here. The motor will turn this, but there's a lot of friction in this system. So the first thing we're going to do is try to make some positive feedback so that when it's on, as you spin it, it'll try to cancel all the friction and spin as if it's frictionless. Okay, so what that means is, of course, if I tap it right now as it's off, it stops right away. But it can use the sensor that senses how fast it's moving to add in additional torque to try to cancel all the friction. Okay, so we'll see that here as I guess I have to build this thing. So in this block diagram, I'm not going to explain too much about the block diagram. It's sensing the outputs, and it's feeding back the velocity into the motor itself. So when it's on, like it is right now, it's less, you see it slides a little better than it did when it's off. And I like to actually increase that feedback and make it even seem more frictionless. So we can do that by just changing a little variable here. So the feedback was at something like 70. We can go to 80. And we see, again, when it's off, so it's still off, but the moment I turn it on, it's as if it's a frictionless surface. Okay, it's a little bit sensitive. Sometimes it accelerates because our models for the friction and everything are simplifications, right? The viscous friction isn't exactly linear. Okay, but anyway, close to. In fact, I'll turn. Oh, we have it at 80. Yeah, that's pretty good. Okay. In fact, I kind of like it a little higher. So let me do it at 85. Okay, but now it has a tendency to want to take off, so that's a little too high. I'll put it a little bit back down. You see, if we have too much positive feedback, it wants to just keep accelerating, right? All right. So maybe something like 82. Is it what? We get to pick all the feedback loops. Right now, it'll do whatever we tell it to, but it has no feedback except this one thing going on. So, okay. So now let's put the pendulum back on. How long did you balance it? 10 minutes back there? No. I actually have a hard time balancing this thing on my finger. It's so short. Oh, did you want to see it? Yeah. Show us how you can do for comparison. All right. Good. All right, so let's put this back on. Okay. Now we are going to design the feedback together, and hopefully that doesn't log out on me. So what we're going to do, the goal is this, right? We're going to have a controller And that controller is going to take both of these as inputs. All right, and it's going to control the torque. But it's also going to have another input signal that we can specify, and it has an objective. The objective of the controller, let's say there's some input signal that also goes into the controller. And the idea will be that we want the pendulum, first of all, to stay vertical, very stable. And then we want the position to follow our input signal. So we should be able to say where it goes. And it should move over there. All right. Now, we've talked about systems with scalar signals. Everything we've done in this class is scalar signals. And yet, we're looking at a feedback system that has two separate signals feeding back. Okay, you can think of this as a vector of dimension 2 signal. We haven't learned theory related to that. We could, but I'd like to use a theory that we've done in this class. So what we're going to do is separate this into two separate problems. We'll first focus on this problem. We have our system. We have an input torque, and all we get out is it's a function of time, and all we get is the angle. So this one here, which we'll call theta. This one's theta. Okay. So we won't use the other signal for now. We'll just use the angle signal to try to stabilize it, and we won't worry about controlling the position. Okay. So this is a single dimensional signal. Should be stuff we can handle. I'm going to have some x of t here. So the first thing we should do is understand something about what is that the physics of that pendulum system. So we're going to have some feedback. I'm going to put a little constant. So here's our pendulum. I'll leave this feedback loop unspecified for now. Something's going to go in there. All right. So we can look at the physics of the pendulum, and we'll see that this is actually a problem in the textbook, if you want to refer there. And you imagine that you have, in that problem, you say you have a cart, and you have a pendulum resting on the cart. You have some mass at the top of the pendulum. And you can control the acceleration of the cart, a of t. And, of course, you get the same angle measurement that we get here, theta of t. Okay. Now, if you look at the physics, it's pretty straightforward. You have gravitational acceleration and a sine of theta of t, because this is representing sort of the component of the, you have gravity pointing this way, and it's the component that's orthogonal to the axis of rotation. And you have something like this, the acceleration that you apply, which has a cosine of theta of t multiplied by it. And this equals the length times the angular acceleration of this. Okay, so let's start from here and see what we can do. Now we want to control such a system that has these dynamics. The first thing we're going to do, after noticing that this is nonlinear, you see this is a sine of our signal, theta of t. We don't deal with stuff like that, right? We're learning about controlling linear time invariant systems. This is nonlinear. But I mentioned that one of the tricks that's used to turn a real system into a system that we have the math for is to linearize. So you linearize around the point you want to operate, and that point is the vertical point. So we're going to say that the system, for very small theta, acts almost linearly, and if you do the Taylor expansion, you get, oh wow, we're out of time here. You get that sine of theta of t. Oh no, we have 10 minutes. I thought we were already done. All right, I think we can do this in 10 minutes. All right, that approximately equals theta of t, and cosine of theta of t approximately just equals 1 for small, or 0, sorry. what am I doing here? Yeah, 1 for small theta. Okay, so using this approximation, then we get that g theta of t minus a of t equals L d dt squared theta of t. And this is something that we can deal with. Taking Laplace transforms, we get g theta of s minus a of s equals L s squared theta of s. And here what we'd like to do is say that, well, let's move stuff over. We get g minus ls squared theta s equals as. All right. And finally, theta over a of s equals 1 over g minus ls squared. All right. Why do we care about this ratio? Because for this system, y of s is the output. The theta is the output, so that's y. And acceleration is the input. And so our transfer function of this system, after linearizing, is just the following. Thank you. Yeah, that took too long. Sheesh, thanks. All right, so so we get a system like this, and it's got, if we want to split it into its poles, we would say, you can rewrite this as, well, what are the poles of this system? The poles are plus or minus square root of g over L. And you can then rewrite this as a minus 1 over L s plus square root of g over L s minus square root of g over L. Okay. Bottom line here is, well, we're not going to go measure the length. In fact, this particular diagram doesn't exactly fit our story because the mass isn't all at the end. It's distributed along the length. Okay, you'd recalculate, but the form of the function would be the same if you actually did the physics for this. And that means that aside from the constants g and L, the main takeaway from this is we have a two-pole system. We have a pole at positive some number, I'll call it alpha, and at negative alpha, where according to the above derivation, alpha would be square root of g over L. But that's not, again, we don't know the constants, but we do know that the system has these two poles. Okay. Now, it's a causal system, so the region of convergence is to the right of here, and therefore it's not stable. And we know it's not stable, right? I can verify that just to check the physics. Okay, so this is not a stable system. So what we're going to do first is say, what if we put proportional feedback? What if I just do this? I make this thing minus k. I'm going to put a subscript 2 just because of the way the variables are labeled in Simulink. So minus a constant times whatever the angle is. So this is going to, if you think about what this feedback will try to do, it will try to put a torque in the opposite direction of the angle so that it'll bring it back up, right? Now, we can mathematically see what would that do to this system. Okay. So let's put some labels on there. Let's go up here. Where was it? Right here. First of all, let's write in here what the transfer function is of the pendulum. We already said that it's something like c over s plus alpha s minus alpha. Okay, we know that's the form of this thing. When we look at the Laplace transform, this is x of s. This is minus k2 theta of s. And you add them together. You put them through here. What comes out here is c times x of s minus k2 theta of s over s plus alpha S minus alpha, right? And that has to equal theta of S. So there's our, now we've formed a, we've looked at the block diagram that contains our system, and we've just calculated out the equation that the feedback loop gives. Okay. Of course, what we want is theta of S over x of S. So we have to do some manipulation. For lack of time, I'm just going to jump through the algebra. And what we get is theta of S over x of S equals C over CK2 plus, I didn't skip all the algebra. We can do this. And we can find that it's C over S squared plus CK2 minus alpha squared. Okay, and finally the poles of this new system, okay, containing the feedback loop, right? The poles are plus or minus square root of alpha squared minus CK2. So all we've done by adding the proportional feedback, we've changed the poles, but we've changed them in a way that's still symmetric. Our poles are still plus minus some number. But notice that this number might be real, it might be imaginary, right? It's real if your proportional feedback is small. But if your proportional feedback gets big enough, the inside this square root is negative, so you get an imaginary number. So what's going to happen is as we increase proportional feedback, we're going to get the following behavior. These poles will move. They'll stay opposites each other, but they'll move in like this. And if we increase the feedback enough, they'll come up, they'll be purely imaginary, and they'll come up like this. So can we make the system stable with this kind of feedback? It's never going to be stable. It'll be almost stable, right? So let's do that. I'm doing this because they have a max angle. It'll shut off if it goes too far to the side. Okay, so that's pretty good, actually, right? So it turns out that the friction in the system actually helps you slightly. So our theory was saying that it won't be stable, but it'll be like really close to being stable. But we have some simplifications in the model. So it actually will be somewhat stable, but let me show what happens when we increase this. So what if we do something like 5? So remember, that should have brought the poles up the imaginary axis. So we should have something like this. So it should kind of have a resonant frequency where it oscillates a little bit higher frequency than it did before. Right? Okay. So you see that happening there. Okay. Now let's do one more thing with the theory. Let's see what happens when we put in. See what happens if we add a different kind of feedback as well. So we're now going to have same thing we had before. This was our C over S plus alpha, S minus alpha. But then we have now two feedback loops. One of them has a derivative. So we're going to feedback both proportional feedback and derivative feedback. Okay? So what that means is if this was theta of S, then this here becomes S times theta of S. Okay? We're going to add this in. Of course, you can do the same exercise to see what happens to the poles and zeros. And in fact, again, lack of time, I'm just going to jump right to what the poles are. I hope you know how to do this. Just go through and label everything, feed it back around, get an equation, and factor it for the poles. Okay? And what you'll find is that we'll call this thing will be K2, or no, K4, and this one is minus K2. Okay, and we'll do, the poles are at CK4 plus or minus square root. You can see that I used quadratic formula here. Plus 4 alpha squared minus 4CK2. Okay? Now, the important thing about this is the following. You have two poles again. They're centered the poles are centered around a point around CK4 over 2. Oh, it should be a minus, negative. Okay, so, but again, they're going to have a plus and minus, either a real part or an imaginary part. So what you're going to have now is poles like the following. Because you have the proportional feedback, you have a point here, which is minus CK4. That was our derivative feedback. And you have the poles are going to be centered around that. They'll either be here or they'll be here, depending on whether the proportional feedback is big enough to make this thing positive or negative. Okay? So we can possibly make it stable with the combination of these two things. All right, so let's do that. I'm going to decrease that one to 4. I didn't like it so high. And K4, we need some of this to be somewhat small, if I remember. All right, let's see if this works. Oh, that's pretty good, actually. Okay, so it's actually doing a very good job of keeping it stable. Notice it's not doing anything with the position. It's actually still acting like it's a frictionless surface that is just wandering around on, right? Wow, that's better than I expected. Wow, okay. What'd you say? Well, then what we're going to, so I'll show you that right now. So then what we do is we say, we've used theory to stabilize this thing. Let's, oh, there's the pen. Let's pretend this whole, so remember we had two sensors, right? We're going to put this whole system in one big box now. This is our stable pendulum. We're no longer going to use it's got feedback control and all sorts of things going on inside. We don't care. We're going to assume it's always going to stand up tall. And it now has a position sensor that we're going to use as the output. Okay? And again, we still have our torque input here. And so if you have torque going into some system that torque being an acceleration, right? And the system now is just some solid structure, frictionless. Well, position is going to be a double integral of torque, right? Okay, because acceleration is the second derivative of position. So this whole system, just by the definition of torque and position and assuming it's a frictionless surface, we get it's a 1 over s squared. That's the transfer function of this system. Now what we'd like is, with some feedback, we would like to have an input here that's x of t, and we would like the input to the output to be stable. In fact, we'd like it to be a tracking type of system. So again, we can look at what happens if we do negative proportional feedback. And we should recognize that this two-pole system is just like the first system we were trying to stabilize. The first one had two poles that were if we remember from up here, the first system had two poles that were opposite each other. This system has two poles at the origin. But if we work out the math for the same reason, by adding proportional feedback, we're only going to cause the poles to go up and down the imaginary axis. And it won't actually make it stable, so we can try something like that. We'll just use K1. And if I remember right, I don't remember the values that work well here, so I'm going to keep it not too big. Okay, so now it should try to recenter, but only using proportional feedback. So again, we should see the same sort of oscillation going on. Let's see once it gets up here. Okay. Ooh, See, it's sort of unstable. Let's do that again in case you didn't catch what was happening. It's okay. So what's happening is it's not only trying to balance, but now it's trying to center itself here, and is doing it in sort of an unstable way, so it's going to keep oscillating back and forth. See, if I recenter it, then it's okay. But once it starts getting off, it kind of, you see. So the proportional feedback, again, is not able to make it stable by itself. But lastly, we'll do the same thing we did for the first system. We're going to add derivative feedback as well. And that is called K3. Again, I don't remember what values are going to work here, so we'll just... There are some built-in values we can switch to. Although I think we got the stable part much better than the default gets it. Okay, so these values are holding up the pendulum very nicely. So let's see what happens with this. Nope. Okay. All right. You can see if you had more than 1 minute, you could actually work out some good values to use rather than just trying it. Okay, let's put their default values. Okay. Oh, whoops. Right. Sorry. All right, so I've loaded their values. I have to admit, though, I don't love how I don't think it works as well as you could make it work. But anyway, it's pretty good. Actually, that is pretty good. Yeah, that works much better. So you see, and now we could actually turn on signal generator and make it follow some pattern. Right now it's just trying to recenter at 0. But we could tell it to... you see, this is what I don't like. It doesn't ever actually sit there still. It goes back and forth a little bit. So we could turn on something like this. We could do... Yeah, so this is going to do like a square wave, which means it's going to tell the position, move here, like that. Okay, so... Might not be telling it to move very far. I should increase that amplitude. You can see it's sort of doing it, but it's hard to tell whether that's just it trying to balance or it's actually doing it. So let's change this to 10. All right. And oh, yeah, so it's not even... Oh, maybe I've... oh, you know what? Maybe it's because I turned this thing off. That's probably it. Okay, you're free to go. I'll let you... Those who want to play around with this can stay and play a little more.